So this is our website. You're welcome to look at it. We have a vast array of animal imaging equipment. We have optical imaging. We have a Xenogen. We have a CRI, which is a near-infrared fluorescence imager. I co-direct this with John Frangione, who's an expert in optical imaging and radionuclide imaging. We have a micro-PET, micro-CT, and a micro-SPECT, micro-CT. We have 4.7T MRI, and I'd like to show you here, this is an example, very similar to what you see clinically. This is a fused, co-registered micro-SPECT, micro-CT image of a mouse with an agent that visualizes the thyroid. You can see the thyroid and the heart here. Now, how do you do this? You have to do dual modality. They turn out to be in the same here, so they're done simultaneously. You inject the radioisotope. In this particular case, you wait for it to clear. You take the CT to see the skeleton. It gives you an anatomical reference, because if you didn't have the anatomical reference, you couldn't identify the thyroid or the heart or whatever. So this is the advantage of multimodality images. It's been used clinically. There's PET-CTs that are very popular. It's gaining traction in the preclinical cancer field as well as other fields. And we'll come back to this. And I'm going to talk a little bit about this MRI here. So we have two, soon to be three, like Al. We seem to accumulate MRI equipment very casually. And I can still count on one hand how many MRIs we have. We don't have as many as you. So these are on the 7th floor of our research building. That's a very important point. The radionuclide scanners are in the basement because they have to have lettered rooms. We'll talk about the regulatory challenges associated with doing radionuclide imaging in mice. It turns out they're more drastic than human radionuclide imaging. And so they take a lot of room. These are big magnets. And so for those of you, I thought it's late in the day, maybe inject a little bit of humor. Those of you who are not familiar with Onion, Onion is a tongue-in-cheek website that makes tongue-in-cheek things about science, news. It's very irreverent. So this is their idea of a big science machine. Okay, so this is a human down here. And what happens in this giant machine creates science. And you can read while I tell you. The reason I show you this slide is I give a lot of talks to radiologists. We were joking before about whether radiologists really understand the physics of MRI. They probably don't. And I talk to a lot of cancer biologists. And I realize, as Al said, you know, they need us. We're priests, sort of. And to them, MRI seems like this big science with all these complicated things in it and very intimidating. It's the most complicated of the imaging modalities. We might get some arguments from the radionuclide people, but not true, because you can make any kind of contrast you want. In fact, the joke always used to be, you know, there are 1,000 ways to make MR images and 999 of them are bad. We have to figure out the one good one. You can make them any contrast you want. There's no universal grayscale. And you really have to know what you're doing to highlight what you're looking at. And I think it's been incredibly intimidating to the cancer biologists to get into this, because to them, these machines are big. They occupy large rooms. Bad things happen around them. And you need to talk to crazy people like MR physicists. I'm a chemist. I can talk to them too. And sort of try to understand what they're telling you. They write these great equations out. They talk about T1 and T2. It's very important. The saving grace for diagnostic MR is you don't have to understand the physics to interpret the images. And if that weren't true, I don't think MR would have been adopted as far as it has. So this is what I think. I don't know, but I look into their glazed eyes while I'm talking about MR physics, and I imagine this is what they're thinking about when I say MRI. Big, giant machines in big rooms making complicated, big science. So why use MRI if it's so complicated? Because there's no ionizing radiation, and for humans that's important. It turns out to be very important for animals as well. There's excellent soft tissue contrast. It provides, in the same imaging modality, you've already seen examples of this, superb anatomical detail and superb functional imaging. And there are many examples of it. But it's complicated. As you know, it's very complicated. It's pretty expensive relative to the other imaging modalities. When you add up the operating costs, the citing costs, and the experts you have to use it, and this used to be true, and it poses safety issues in citing, and I'll show you some examples. But if you look in the literature, and you just go to Science Citation Index, and you say, how many citations are there for MRI and murine models that got here, it's growing, and it's growing exponentially, and it'll continue to grow for the same reasons I just told you. It's the most useful anatomical imaging modality. It's much better than CT. You can't run high-resolution CT without frying mice. The radiation dose gets very, very high. And the trends are that it's gaining wide acceptance. If you go to this meeting, you'll see more and more MRI images. You go to the oncology meetings, you'll see it. And there are an increasing number of studies using dual modality imaging, like that SPECT CT or PET CT, but in animal models. And so we had a lot of demand to do FDG PET MRI. And I'll try and give you the rationale for why we did that. But before I do, let me just quickly show you that we can make many, I'm not going to go through the slide in detail. Al showed you can gate, respiratory gate, you can cardiac gate, you can get excellent images of the cardiac. This is done on a 4/7. And you can look at cardiac function, you can do hyperpolarization, I don't have time to go into it, but you can make excellent anatomical and functional imaging on these high-end machines, these 4/7s and 7 Teslas. And then you can use all of these software programs that exist. At Harvard, we use 3D Slicer. There are many other software programs around to co-register them and show and highlight what you want to do. You can make movies. You can do whatever you want. So that's animal scanning. Before we had animal scanning, and when it was difficult to go down and get on the animal scanners, we would actually do animals on our whole body scanner. Now, why would we do that? Because in the clinical arena, the clinicians have optimized contrast to the point they know how to diagnose almost every disease, every tumor that you want. So if you want to look at prostate cancer, I can tell you we have a protocol for prostate cancer on our 3T system. It almost translates perfectly to mice, as we'll see, and so it's easy for us to do. The only thing we have to do, here's our whole body 3D research, whole body 3T research scanner. It happens to be a GE, sits in a large room. It actually looks like a pretty gigantic machine. And we can build this little coil, which we've actually published many papers with. It's about this big. You put a mouse or a specimen in it. You put it in the scanner. If you're creative and more intelligent than I am, you can actually make 4 coils at once and do a mouse motel and increase your throughput. But you can get very nice images. And one day, someone said, well, what about doing an orthotopically implanted mouse prostate? And these are the images. They don't project well because they're heavily T2-weighted images. There you can see the mouse tumor on the sagittal slice. Here's the bladder. And here you can see the mouse tumor here. All these other structures are very complicated. They don't look anything like human prostates, and I'll show you that in a minute. And that's another challenge for us. But the contrast is fantastic. When you open up this tumor and look at the gross histopathology, it looks exactly, it's septated just like it is here, and you can see the septations. So these are heavily T2-weighted scans done on our clinical scanner. What's the problem? Nothing's optimized to do animals. You can't gate, you can't do anything because the respiratory rates for humans is much slower than mice, and the cardiac rates are much slower. But citing one of these is a nightmare. I mean, if you look at it, this sits in a 600 square foot room. You have to post signs at the 5 Gauss line for people who have cardiac pacemakers. You can't walk into that room because you're always worried about screening people for metal. It's really a safety issue, and it's dramatic, and it's expensive, and it's heavy, and it's big. It's like that big science thing. And here's what happens sometimes. People forget that they're fringe fields, and sooner or later you have an accident. And if you want to have a chuckle, go to YouTube and look up MRI safety, and you'll see video after video of things getting stuck in the magnet. Once they get stuck in the force is enormous, and it's dangerous, and people get hurt. And so that's a safety issue with these big magnets. Because someone asked about fringe field and shielding. This is a self-shielded magnet. The fringe field's still high. I can't walk in with my cell phone. I can't walk in with my wallet. And I have to worry about it. So we'll return to that in a second. So those are some of the issues you deal with, but let's talk about practical regulatory issues. When you're dealing with animals, it's complicated. Most animals, the transgenic mice we use, are behind barriers. You can take them out once, you can't ever bring them back in. So you need a holding area somewhere to hold them if you're going to do longitudinal studies. You can never take them back behind the barrier. It's just too expensive and too dangerous. The pathogenic jeopardy is high and huge, and making and maintaining these transgenic mice, many of you know, is very expensive. It gets even more complicated when you inject them with a radioactive material. You have to have a leaded holding area, and you can't transport them anywhere in the building. They have to stay in the licensed room as long as the radioisotope is still active. It's much more complicated than dealing with people. So you just can't take them outside the barrier. So there's housing issues and handling issues, and longitudinal studies become quite challenging. So why do we need a desktop MRI? We have this whole body scanner. We got 4.7, we have 7T, we'll have a 9.4T, because we have regulatory restrictions associated with radionuclides. So when we first started talking about doing MRI PET, our MRI sit on the 7th floor, our micro PET sits on the basement. We don't have a cyclotron. We buy our FDG locally from PetNet. They would not let us take the animal up 7 floors for regulatory reasons. Now, it sounds like not a big problem. It's an enormous problem. Co-registration is another issue. 4-legged creatures have internal organs that move a lot. 2-legged creatures don't. So if you don't position them in exactly the right way and maintain their positioning, which sounds easy to do, but in practice is very hard to do, co-registration is an issue. And then let's not ignore the safety, no fringe field. When you see the magnet, I'll make some comments about where the fringe field is. We take it for granted, but it's incredibly important that there is no fringe field in this magnet. So here's Al showed you his site. Al, you can drive your forklift truck down. We're in the basement. You'll have to go down some stairs to get it down there, but I'm sure you can drive it down the stairs. So here's our system. There's the rack. You've seen it before. Here's our M2 magnet. And I have to tell you, it's not in a very big place, and it's in a room that's shielded. You need a radioactive license. You need a badge to get into this room. Because you'll see in a second, we have a micro PET and a micro CT right beside it. And people who walk into this room always ask me, the radiologist, where's the magnet? I'm usually leaning on it. You can put your credit cards, your wallet right on top of here, and you can put your telephone, your cell phone right on top of here, and nothing happens. I've done it. You cannot do that in our 3T system. You'll only do it once. So what about image quality? You know what? We have a 1.5T clinical scanner, so I can take the same mouse and image it at 1.5T and look at the image quality. These images are pretty good. There's an internal T2 standard. These are the hardest images to make well. T2 weighted images. And the kidneys are an internal reference for it. I don't know if you could project well, but look at the zonal architecture in these coronal images of a mouse kidney. They're beautiful. No contrast. Intrinsic T2. That was spin echo. This is fast spin echo. Those were 25-minute images. These are 4-minute images. You can again see the zonal architecture here very nicely. Not the same resolution, but good enough. Very nice. If you can make these kinds of images on an MR scanner, the scanner's working well. This scanner works well. Here's just another slice. Now I show you this because this is our tech. I'll tell you who he is in a second, our common mouse holder. And here's our microspec, and hiding behind here is a micro PET, micro CT. There's a leaded door that closes, and here's the magnet, no fringe field. You don't have to worry about anything. And it's literally 10 feet away. So what do? We have a lot of interest in doing micro PET, micro PET, micro MR, so we use a common mouse bed. Same bed between the two scanners, keep the mouse anesthetized. We pre-inject the mouse. It takes about an hour for the FDG signal to background to clear, and then meanwhile we do the MRI, so we don't have worries. We have no issues about transportation, no issues about co-registration because the mouse doesn't move here. And here's the first application. This is an application which we used, now we're interested in, we used it as a test case, doing FDG PET MRI of brown fat in a mouse. Now there's two kinds of fat in a mouse. There's white fat and brown fat. Brown fat's metabolically active, and we'll see why that's important. And so here's our T1 weighted protocol, spin echo, and very nice images, really high quality images. Now FDG is very interesting here because for many years people thought brown fat was not metabolically active. It uses glucose very nicely. And in fact, you can differentiate the brown fat from the white fat in a second, I'll show you, because the brown fat is FDG avid and the white fat isn't. And the way FDG works, it just gets taken up and phosphorylated. For those of you not aware, if you are, I apologize for the redundancy. And you can actually see the glucose uptake and utilization, and it gives you an index of glucose metabolism. So here are our first set of images, common mouse bed, MRI, PET. Here's the FDG PET. If you had this by itself, you have no anatomical reference. Here's the MRI with the arrow showing you where the brown fat is. Look at the white fat. The white fat does not use FDG. Here are the co-registered images. Here's a different slice. You can see the heart taking MFDG co-registered. No special tricks, straightforward co-registration. Enables this experiment to happen. If we had to, we can't take it up 7 floors to our 4-7, and if we could, we'd have to use the common mouse bed. It's hard to schedule them at the same time. The animal would move. The co-registration would become difficult. Here's just another example. And I hope these convince you that the proper orientation and scaling is relatively easy to do because the mouse doesn't move between the two studies. The last example I'll show you is a tumor example. And Otto Warburg in 1931 described the Warburg effect. The cancer cells will undergo glycolysis. They'll preferentially take glucose and make lactate even when they're completely oxygenated. The so-called Warburg effect, and tumors do that. So most tumors in humans are FDG avid. They take up FDG and they light up on FDG PET. And we had an interesting project here, which is being presented at 3 o'clock tomorrow from our group. Akash Patniak and Luke Cantley are the two cancer people here. Many of you may know Luke Cantley from his tyrosine kinase work. And they had a genetically engineered model of spontaneous prostate cancer in male mice. And they were interested to see, could we do anything with imaging to look at treatment response early on using antiangiogenic treatment or specific targets along the genetic pathway that's altered in these mice. Now, it turns out mouse prostate is very complicated. I just show this to you to show you there's kidneys. The mouse has all kinds of organs that the human doesn't have. It has seminal vesicles here, but it has coagulating glands. They threw us off for a long time. There's a bulbourethral gland here. The testes are here. And it's really complicated to see the prostate. It has nothing like the anatomy in a human prostate. And this is one of the things that you have to learn is you have to go back to mouse anatomy. Al has nice atlases of normal mouse anatomy, very, very helpful here. But you need to go back and learn how to do it. And here's the mouse prostate, and it's very complicated. Anterior and ventral mean different things here. Ventral means the front, dorsal means the back. It's almost like anterior, posterior in humans. You can see the urethra, and you can see all these ducts going on. So we started imaging these, and we did spin echo intermediate weighting just to see them. This is our protocol. Just a standard protocol, 40 slices, takes about 25 minutes. And here's the T2 weighted MRI scan. Here's the FDG PET scan on exactly the same mouse. And here's the overlay. Now, I will offer that I can't interpret the MRI without the PET, and I can't interpret the PET without the MRI. Why? This is an active tumor nodule on histopathology. It sits right over here. You see it in the overlay. You see all the rapid bladder clearance of FDG here. If you didn't have the MRI, you would never know that this was a tumor. You wouldn't be certain. If you didn't have the FDG, you wouldn't know that was a tumor nodule, unless you did the gross histopathology. Here's another example. Here's the T2 weighted MRI. Actually, very high quality images done with the mouse body club. And you see the nodule here. You see the hyper intense signal in the FDG PET. There's the bladder signal. That's sort of the reason why FDG PET's not used in humans. And here's the co-registered image. Look how well this co-registers. Again, if you didn't have the MRI, you might not be able to interpret the PET. And if you didn't have the PET, you might not be able to interpret the MRI. Now, this co-registration is using image analysis software developed by the Bioscan system, which is actually OEM by Mediso, provided by Invicro, and these are the websites. You can email me if you're interested. And we use this package to co-register the aspect in the Bioscan PET images, even though there's some issues associated with DICOM headers that we had to solve. So what does the aspect 1 Tesla do for us? It provides, as you've heard from others, a very high image quality at 1 Tesla with an easy-to-use user interface. Very safe and easy to cite. You can virtually put it anywhere. You can move it. It's on wheels. It's heavy. You need to call Al. He'll come with his forklift truck and he'll move it for you. But the main thing it does is it enables this easy-to-use, safe, convenient, and compliant. We're violating no radioisotope restrictions. We can get PET MRI at the same time, and our throughput's high. We can do 8 to 10 mice a day using this for multi-modality imaging. So what does it do for this PET MRI? As I said, you need both. It's regulatory compliant. It really simplifies the workflow, and it provides the simple, easy way to do co-registration in fusion. Now here's an analogy I like to use. In my world, these big MRIs are like the old mainframes. Very useful, take up a lot of space, have a lot of computing power. I think of it like a laptop MR. You can take it to where you need it, and it's very convenient to use. You don't give much up in computing power today. You have 1 Tesla images. You've heard examples where 1 Tesla is good enough or better than 7 Tesla. It's great for us because we couldn't do these studies unless we had this machine exactly where it is. Now, I'm doing all the talking like Al. I don't go down there very often unless there's a big problem. Laney Lunsford was actually trained by the Aspect people in Israel. This is Kyle Robichaud. These are 2 technologists. They run all our animals. They're very happy with the Aspect system. They think it's a robust, reliable, easy to use. They don't let me anywhere near it, which is probably good for Aspect. And my collaborators are the people you saw, Akesh Patniak, who's actually an oncologist, cancer biologist, Luke Cantley, and John Frangione. And I hope you understand how useful and valuable the Aspect MR is to our multimodality imaging at the BIDMC. Thank you very much for your attention.